Okay. All right, there we go. So let me message Francesca back. Oh, look, she's here, I think. All right. Welcome, Francesca. How are you?
I'm good.
Good. Okay, so what we've done so far, we're going over the homework from last night. So we did 1A and B together in class. And then there was some question about like if we did the chart right for number 2. And so we filled in all the values of the chart. In order to do that, we set up our formula so that we could S in every time instead of having to stick S in over here and then do a bunch of solving every time. So we got 10, 6.7, 5, 4, 3.3, 2.8, and 2.5 as our answers. So I'll leave it like this for a minute so you can copy it down. And now we're about to do 2A and plot these points. Oops. Okay, so I've copied down the grid, the graph from the original document. And I've tried to put in my little tick marks as well as I can. And now what we're going to do is we're going to take each of these points and we're going to plot them. So we have average speed is 50. So I need to go up to my average speed being 50. So here's my 50. And I need to go up to 10 hours. So I'm going to put a point at 50. Then I'm going to take my next speed was 75. That's halfway between here. And 75 goes up to 6.7. So it's like almost 7. Then we have 100 being at 5. 150 being at a little over 3. 175 at 2.8. And 200 at 2.5. Okay, so we end up with, I did a bad job. We end up with a curve that swoops down like this. Okay, what questions do you guys have about that? Is that what you got as well?
Yeah, I got that.
Perfect. Okay, so we should get this. And then it says write a function rule that shows how to calculate race time as a function of average speed in the Daytona 500 race. That's what we did right here. Okay, so race time as a function of speed for the Daytona 500. It's always a 500-mile race, so that 500 won't always be there. So part B, we kind of did to solve part A. Okay, so what questions do you guys have?
I don't have any questions.
All right. Okay, Francesca, do you feel a little caught up?
Yes.
Okay, I'm going to post obviously the video recording of our meeting, and also I will post a PDF of my work that we do today, so you can always go back and look at it again. Okay, so in number 3, what do you guys think about number 3? Did you have any questions?
Well, was you supposed to use the data from the first question?
For number 3?
Yeah.
So it has 1960, 61, and 97, 98. So in the first one, yeah, we have 60 and 61, and we have 97, 98. So yeah, it's referring to these two pieces of data. You're right. And it says, it says that the difference in average speed for both of those are 25 miles an hour. So if we look, 125 to 150, the difference in those speeds are 25 miles per hour. And 148 to 173 is also 25 miles per hour. Okay. So it's saying that those two things were the same, but the time differences were not the same. So the time difference here, do you guys remember what it was? I don't have it written down.
It was 4, and I think.
Yeah, this one was like 4 hours, and then this one was like two-ish, maybe. Say it one more time.
It said 3.3.
Okay, yeah, so 3.3. So that's a pretty big difference, but they had the same difference in speeds, right? This one went 25 miles per hour faster, and this guy went 25 miles per hour faster. So it's saying, how is that illustrated in the shape of our graph? What did you guys say? So, for example, so what was it? 125? These are the same x distance apart. So like this is the same distance. And the other one was like 150-ish to 175-ish. So that's like from here to there. So like, do you see how these x distances are the same between those guys? But then the y distances, this is much bigger than that, right? So our graph is showing that statement that they made because at first there's a steep curve between points. But as you go down, that curve gets less and less steep. Okay, so we see a curve that has a slope that gets less and less steep as we travel equal distances. Oops. Along the x-axis. Let me, there, hopefully that helps. Okay, any questions about that statement that we just wrote down?
No.
All right. And then in part B, it says, how are the table, graph, and function rule relating average speed and race time similar to or different from those you've seen in earlier problems and seen in work on earlier problems? So it's basically saying, like, we looked at a table, a graph, and a function rule, excuse me, and it's asking how are these things similar to or different from other inverse variation functions we've looked at. Like last week, we looked at a bunch of inverse variation functions. What do you see that's like different or the same?
I would say that they're both decreasing.
Yeah, so this function decreases over time. Some of the other functions we've looked at don't always do that, and some of them do, okay? One thing that I see is that this one has a very specific constant of proportionality. So, and has the specific constant 500, which is going to change how our function looks. So I'm going to show you something on Desmos. So our function is, I'm just going to change things to x and y so that doesn't use. So y equals 500 over x. So if I graph that on Desmos, you can see that graph right there, yeah? But let's pick a different constant of proportionality. So pick a different number, something really small or a lot bigger than 500. Somebody pick a small number.
3. Maybe?
Yeah. So 3 over. So that's the blue one. Look at how different the blue and the red functions are. So the blue is a lot closer to the x-axis and the y-axis than the red is. So that constant of proportionality is going to change the way that your graph and the way that your relationship is. Okay, so that makes a pretty big difference. Then, so that was number 3, and those are just more like conceptual questions. Then number 4 and number 5, what thoughts did you guys have about 4 and 5? We'll start with 4. Let's write down what you guys thought. So it says the race time is, so this is part A. The race time is blank proportional to the average speed. What did you guys say?
I put inversely
Good. Why'd you say that?
because like in the graph it shows like how the speed and the distance and time all like, I don't know how to explain it.
That's okay. So do you see how the time is here, but then the speed is on the denominator of this fraction? When you think of inverses with fractions, you're flipping things, right? Like the inverse of 3 is a third, the multiplicative inverse. So this is inversely proportional because they're equal to each other, but you have to have the inverse. It has to be in the denominator, and you have to have some sort of constant of proportionality. So inversely proportional just means that you have one variable equal to another variable in the denominator of a fraction. Also, the whole activity is called representing inverse variation functions, so you can guess pretty well with that. So with a constant of proportionality of, what was the constant of proportionality?
500 miles.
Yeah, very good. So the constant of proportionality is just the number that makes the relationship between the two variables happen. So constant of proportionality was 500, and it says the average